All right, friends, welcome to school. And I know that you're pretending it's a snow day, that I'm not there, you don't have to do anything. But haha, JK, you actually have to do something. Because we're not redoing this tomorrow, I'm just going to kind of proceed with the understanding that you already understand this. So we're looking at polar graphs. We're just going to take 2 more days to kind of look at some kind of weird graphs that we get. Think about why they are the shape that they are. Practice them on our calculator, but be able to do them in our brain by recognizing the pattern of the formula and what the different parts of the formula tell us. Because on the test, we won't have our calculators, we'll just have our brains. So these are going to be the first thing. It says polar graphing is fun. So remember that. Keep in mind that since it's circular, meaning the graph paper is circular, it eventually traces over itself. You're plugging in theta. All you can do for theta is plug in values between 0 and 2 pi. Even if you keep going, you're just repeating the outputs. And so after you've gone through 0 to 2 pi, everything's going to trace over itself. So there's some common shapes and polar graphs that I want you to be able to recognize. We saw this a little bit in our notes from 9-6 day 2 yesterday, where I had you practice graphing in polar mode. Keep in mind that when you're in polar mode, you also want to be in radian mode so that you can get your graphs graphed accurately. And when we did these yesterday, we noticed that they were circles. We also did the whole process of turning them into XY equations where we actually could see the circle equation, figure out the center and all that. We're not doing that today. We're just going to make sure that we can start to recognize the graph. So your mode is polar and your mode is radian. All right, so we're going to look at these two formats. You're going to have to recognize the format. So you want to be able to know when you see something in front of cosine and something in front of sine, that's going to generate a circle. And we're going to add to that list the rest of today and tomorrow. So here's an example. Obviously here, this is our A value, and this is the right format. So I would see this on my quiz and go, okay, that's going to generate a circle. Now let's analyze it for a little bit. What's going to be the maximum value? Well, if you think about cosine theta, that always has to be between 1 or -1. And so the most it could be is 1. And if this part has a value of 1 and there's a 3 out front, then the max value is going to be a 3. That's the highest it can go. The lowest it can go is -3. So like the absolute value, the farthest that it can go is going to be 3 units. If you think about where will that happen? Well, that's going to happen when your cosine is 1. That's going to max out your value. So think about, where does that happen? Where is the x coordinate on the unit circle going to be a 1? And have your unit circle out in front of your face to help you. It happens first when theta is 0. It happens again at pi, then 2 pi, then 3 pi, and so on. But again, after I've gone around to 2 pi, it's all repetition. Okay, so this is a different question. Where will the zeros occur? When a 0 occurs, it means when will this whole thing have a value of 0? When will R be 0? So I would be looking at, okay, when is 0 going to be the answer for 3 times the cosine of theta? Well, clearly that's going to happen where the cosine of theta is 0, meaning the x coordinate on your unit circle is 0. So if you went back and looked at that, that's going to happen when your angle is at pi halves. And again, at the bottom of the circle, 3 pi halves. And that's going to continue, except everything from there out will be repetitious. So if we're going to graph these on our calculator to get an idea of what's happening, our window that we've talked about before is going to go from a minimum theta of 0 to a maximum of 2 pi. And we're going to count by, or do theta step, I would say pi 12ths, maybe pi 24ths. So I don't really know where this is going to go, how far, but I would say if I go like from 5 to -5 on my window, counting by ones, and then try that with the y's as well. So make sure you're in polar mode, make sure you're in radian mode, and then go to y equals, which should actually say r equals. Make sure none of your plots across the top are dark. And then let's set our window. So go to window, go from 0, and some of this, if you were involved in what we were doing yesterday, will be the same. 0 to 2 pi, by pi. I probably use 24ths, it looks like. I'm going to go negative 5 to 5 by 1s, negative 5 to 5 by 1s. And then I can type in my equation. And I think we actually did this one yesterday because we kind of cheated and jumped ahead into calculator graphing. So if I type in 3 cosine theta, and I get my theta from the X button, it just becomes theta. It looks like an egg kind of off to the side. But again, if you look at your tick marks, counting up is they're a lot closer together than counting sideways because we're in that rectangular picture screen. So try zoom square, and it should square up to be a circle off to the right. And this is how it's graphed on your graphing paper. And if you can see, on your graphing calculator, if you can see, it goes over 3, and then it must go up 3. And so I end up with, it's got a diameter of 3. So it's going to only, here's the center. So here it'll only go up 1.5, and then here down 1.5. So I'm going to end up with a circle that looks something like this, correct? So 3 is not coincidental. 3 sounds really familiar to me. In fact, 3 is a part of my equation. This number out in front is a 3. So if we did this yesterday, we did get the other equation. We ended up finding out that it was a circle that had a radius of 1.5, which it does, and a center at 1.5, 0. So that's what we have showing here. This is polar graphing. So if I was going to go around and try to figure this out, I would say, okay, well, this line is my 0 line. And according to what I wrote up here, that's going to be one of my maximum points. So here at 0, I'm going to go out 1, 2, 3. And then as I keep going, I'm going to try to fill those in. When I get to pi, keep in mind that's also going to be one of my maximum values. But here's the thing. At pi, I'm at negative 1, 0. So instead of heading towards pi, if pi is my x, if pi is my theta, I'm going to get a negative 3 as my radius. So I'm actually going to back up 3 and end up in that same spot. When I'm at pi halves as my theta, I'm going to have an r value that is going to be 0, because that's the first place here where my zeros occur. So then I'm going to be here. So as you follow those around, that's what generates this circle off to the right. And it never goes on the left because your numbers on the left would be coming from negative values, and the negative values in polar graphing send you in the opposite direction. So you end up with the same picture of that circle. And if you take a peek at that circle, it's a circle that has a diameter equal to 3, which is sort of suspicious because my A is also 3. Okay, so just to go through and do sine, how is that going to be different? Well, it's not going to be significantly different because it's going to be using the same values and multiplying them by 3. But my zeros and my 3s and my max and mins will go in different spots. So think about, where will this have a value of 3? Well, this will have a value of 3 when sine has a value of 1, but sine has a value of 1 at pi halves. So if I go to pi halves on my graph paper, I'll go towards it 3. Sine will have a value of negative 1 down here, but if I do 3 times negative 1, it's going to send me in the opposite direction. So again, I'm back at that same dot. So what ends up happening, grab your calculator, type this in, 3 sine theta. You're going to still have a circle that is a radius of 3, but it's going to be up on the top instead of off on the side. So if I'm looking at these, the one that was r equals 3 cosine theta is a circle that has a diameter of 3, and it is symmetric over the x-axis, which I feel like I can remember because it's a cosine curve. Down here, when I tried the same exact thing, except I started with r equals 3 sine theta, then I ended up with a circle that has a diameter of 3 still. So I feel pretty confident that it's going to just be that a value. But now if you look at the symmetry, this one is symmetric over the y-axis, which again, I feel like I can remember because if it's a sine equation and it's symmetric around the y-axis, I can handle that. So what if it was 5 sine? Well, then it would have a diameter of 5 and be located on, like, going over the y-axis. So we're using our calculators to get a handle on what it looks like, but we're going to have to use our brains to say, hey, what does this do? The a value tells you the diameter of your circle. And then think about what happens when a is negative. What always happens when a is negative? It flips your graph. But you're going to have two scenarios. If I have an r equals a cosine theta, that's pretty messy. But I make it into a negative a cosine. If you think about the graph up here, if you flip it over, it actually flips over the y and ends up being over here. If I had a negative a sine theta, this right up here was my original graph. It's on the top positive part of the y-axis. Now it's going to flip over and be a circle that's still symmetric around the y, but now it's going to end up underneath the y. So you want to be able to just look at an equation and be able to sketch it without having your calculator. That's like your goal. So if you see on the test r equals negative 5 cosine theta, you should be able to sketch or match that and say, okay, this is x. This is, I recognize as a circle equation. This is going to be my diameter, but it's going to be flipped, so it's going to be to the left side. So when I go to sketch this, I'm going to be on the left side, 1, 2, 3, 4, 5, and I'm going to go have my circle be over here, but still centered or symmetrical over the x-axis. So all this jibber jabber in the middle to kind of see where it's coming from, that's exactly that. It's jibber jabber to see where it comes from. What you need to be able to do is say, hey, this is a circle equation. It's going to be symmetric around x or y. It's going to have a diameter of whatever a is, and I can decide if it's going to be on the top, bottom, right, or left based on if a is positive or negative. So you can stop the video and then try that part of your homework, or you can go ahead and do the other part of your homework as well. Okay, let's take a look at what happens if you get an equation that's in this format or this format. Notice the format's totally identical. It's just either sine or cosine. That, my friends, is what's called a limacon. So we're going to think about that. I always think lima beans, and you'll see why. Does anyone even eat lima beans anymore? Anyway, limacon is going to be a different shape, and this one's more complex, but it does have some similarities to what we just talked about. It is still true that both cosine and sine are going to stay within their limits of a value of 1 to negative 1. But now, not only is it getting multiplied by something, there's an additional something getting added or subtracted to it. So it becomes a little bit more fluid in terms of how big it can get. But the max value is still going to occur where your cosine has its max value. So that would be where a plus b then gets multiplied by cosine at its max value of 1. So the highest this can be is whatever a plus b is in its positive form. That's like the farthest you can go, because multiplying it by a cosine value of 1, that's the highest that value can go. And 1 is the highest that cosine can go. Okay, so again, where will that occur? Well, it'll start to occur at theta equaling 0. And like we saw last time, when we go to pi, it actually shoots back and lands on the same exact spot, because if I had a negative r, I have to go the opposite direction. So that's going to be the two places that it ends up having its max value. Where will the zeros occur? That's telling you where r is 0, where it actually hits that 0 as an end result value. Okay, well, let's see. If I had a plus b cosine theta and I want it to equal 0, I'd have to move that a to the other side by subtraction, and then I would divide by b. So you're going to have the zeros wherever you have the opposite of your a value over your b value. And these are all the fun facts that you want to be able to kind of remember, because those will be like, those are solving these equations. So say I had 1 plus 2 cosine theta. Here's my a, here's my b. So I'm going to have my zeros occurring at theta equals the opposite of a over b. So wherever my cosine, let me see here, see if I can make myself some more room. Wherever my cosine theta has a value of negative 1 over 2, that's going to be where I get a 0. So again, I have to think about, where does that occur? And on the unit circle, if I go look, my cosine, or x, will have a negative 1/2 value at 2 pi thirds, 4 pi thirds. So we don't even have polar graph paper in front of us right now, because that might make our brains explode. So let's go to our graph, like our graphing calculators, and let's type in this equation that I just gave you. Let's do 1 plus 2 cosine theta. Graph that, and you should see something different than a circle. Give yourself a second to graph that and see what happens. So what do you see? Well, if I am typing in my 1 plus 2 cosine, and I'm in my good squared up window, I can see that I have, like, it goes out to here. I'm going to make this bigger. I have like a loop in the middle of it. It goes out to 3, which makes sense because my max value is going to be the absolute value of my 1 plus my 2. So the most it goes out is 3. And then it comes out here, but it loops back around. And so it looks like that. It is still symmetric around the x as a cosine problem, which is helpful. And it's still kind of pointing off to the right. Try 1 minus cosine of, wait, what do we have? I'm going to do the opposite. So let's try 1 minus 2 cosine. Sorry. And all we're changing is that negative. So go back to your equation, type in a minus sign over the plus. What happens? Shockingly, it's going to flip over and you're going to have the same shape, but off to the right of your y-axis. So that plus minus is going to flip it over just like we saw the plus minus flipping it over in the x. Okay, so based on what we just saw, everything will be kind of samesies here. Based on what we saw in the circles, take a wild guess what's going to happen here. What will my max value be? Same thing, because the highest sign can be is 1. Where will it occur? Well, where is the sign plus or minus 1, or in this case, positive 1? The first spot's going to be at pi halves. Yes, there will be another spot at 3 pi halves, but because the r will be negative, we'll just end up going backwards onto the same point. Where will the zeros occur? Well, the zeros will occur just like we found up above, where the sign value is the opposite of a over b. So for us, if we did the same 1 plus 2 but sine theta, That's going to be wherever the sine of theta equals -1/2. Okay, well, where's that? Well, that's going to happen at 7 pi over 6. And it'll happen again at 11 pi over 6. So again, we have rectangular. So it'll match what we see on the calculator. So now all you're going to change is you're going to have 1 plus 2 sine theta. Graph that. And not surprisingly, it has a max value of 3 and it comes down and loops around. It is facing up. If you did 1 minus 2 sine theta, you're going to end up, if you go back to your calculator and just change your plus to minus, what happens? Not surprisingly, it opens down. So you end up with the same exact shape, but it flips. So you have to not be focused too much on memorization. You have to be able to say, oh, this formula that has the plus or minus in it makes it a limacon instead of a circle. And the ones with cosine still are symmetric over x. The ones with sine still are symmetric around y. I can figure out the max value kind of through common sense because I know that my sine, where did I just go? My sine is going to max out on 1. So then this must turn into my maximum value, a plus b. So just kind of think through what you know. All right, so let's try a couple different things on your calculator so that we can just kind of figure out what happens because this changes. Let's say our ratio of a over b is less than 1. We already had that. We had 1 plus 2, and then we did cosine theta. Okay, so when we did that, we ended up with a true limacon, and it has a loop in it. So it ended up going out to the side, whatever your A was, and then looping around. That's terrible. Let me try that again. Okay, so this is going to come out here and loop around in here. That happens when this is the situation. How about A equaling B? Well, that would be like 2 plus 2 cosine theta. So let's go ahead and try that. So on my calculator, I'm going to put in 2 plus 2 cosine theta, and I'm going to graph it. Okay, that actually has its own name called a cardioid. I think of it because it kind of looks like a heart, because instead of a loop, it comes to a point. Kind of looks like a little butt. But we're going to call it cardioid instead. Okay, what if your top value starts to be bigger, so now you're greater than 1, but the value stays less than 2? So let's say we had 3 plus 2 cosine theta. Because here my ratio of a to b is 1/2. Here my ratio of a over b is 2 over 2, which is 1. Here my ratio is 3 over 2, which is greater than 1, but less than 2. So I'm going to try again and type in 3 plus 2 cosine theta. And now, if you can see, it moves over, so it does go on the other side. But now you have, it's coming all the way out to 1, 2, 3, 4, 5, if you can see that. That 5 is coming from 2 plus 3, which are the two numbers in my picture. But then it also is coming to a point, or like we call it a dimple because it's not really pointy, it just dips in there. And that's at -1. So this is coming from the sum of a plus b, and this is coming from the difference of a plus b. So in my case, 3 plus 2, that's why it's hitting at 5. And in my case, 3 minus 2, or it should say b minus a, because you end up at -1. And so I'm going to end up, I'll write it there so I remember that I'm going to end up on the other side. So what's happening is like this is moving its way out. Here it's tucked inside of itself. Here it's at a point, and now here it's moving out further, so it's just kind of dimpled in. So if you had to take a wild guess, we'll call this one dimpled. That's the term they use. So we're progressing, and here we're going to have a ratio greater than 2. So we would have something like 5 plus 2 cosine theta, where 5 over 2 is my ratio, and it's greater than 2. So try it on your calculator. 5 plus 2 cosine theta. Now when I look at it, this goes all the way back to 1, 2, 3, 4, 5, 6, 7. But that's because 5 plus 2 is 7. And then this other side, 1, 2, negative 3, comes from my B minus my A. So when I add them, I get that far right. When I subtract them, I get my far left. And if you look at this thing is like a big old almost circle because it just dips in, but very slightly. And so they call that a convex because now it's like almost all going out. Convex limacon. So there's a lot to remember, and yet at the same time not. What if I had done all of these problems using a sine instead? I would have had the exact same results in terms of loops and cardioid and dimpled and all of that, maxes being the sum and mins being the difference. But instead of all of them being symmetric here around the x-axis, they all would have been going like up and down symmetric around the y. So those are the things you want to kind of be able to say is, hey, if I have this, I'm going to recognize those two formats as a circle. I'm going to know that the cosine ones are symmetric over x and sine ones are symmetric over y. I'm going to know that the diameter of my circle is going to be that A value. Great. Then I'm going to have, what if I've got a plus or minus something times the cosine, or a number plus or minus something times the sine? Well, it's still true that the cosine ones will be symmetric over x and the sine ones will be symmetric over y. But now when I'm thinking about my max values, I'm looking at my A plus B. And then when I'm looking at my min values, I'm looking at subtracting those. And I'm going to have, that ratio where if the A is less than B, A over B is less than 1, I'm going to get a loop. If they're the same, 2 plus 2, 3 plus 3, 4 minus 4. So if they actually equal 1, and I'm just recapping everything that's in those notes, if they actually equal 1, then it's going to come to a point and be that cardioid. And then as it progresses to be like, okay, well, it's bigger than 1, but not bigger than 2, then I'm going to get that dimple. And if it ends up that ratio gets even bigger than 2, then I'm going to have what they call that convex, where you can barely see a dimple in it all. So those are kind of the ideas of it, but your job is to be able to look at these equations, recognize them as the shape that they are, and then be able to kind of identify some of the details about it based on the numbers that are in there. So tomorrow we're doing a couple more, so you want to start putting these in your arsenal and really practicing. You've got your conversion equations, limacon equations, circle equations. How do I convert points? How do I convert equations in polar? And then even going back to parametric. So there's definitely a lot to keep track of. Wouldn't be a terrible idea to get a little like note card going or whatever you use that helps you memorize stuff. So hopefully that helps. I will be back for part B, but we are going to kind of just jump right into it and build on what you learned today. Bye.